thing you'll notice is that this is all in vector land, okay? And we found the connection between E and F. It looks something like this. F equals QE, okay? We took two charges, we put them together, and we found that there is a force between those charges, okay? We then said if you take a charge and put it in space, that creates an electric field. This is the relationship between electric field and force. Now, one thing you'll notice is that electric field, that is like the disturbance of space around a charge, and the force only happens when you put a second charge in that field, okay? They're both vectors. This one, however, is global. It exists all in space, and this one right here is just local. As soon as you put a charge in, it's the force on that charge, okay? Now, we also know about this relationship right here from 141. This is potential. Now in this case it's electric potential, but one thing you'll notice about potential is that it's scalar, okay? It's not a vector. Now how do we go from force to potential? How do we go from force to energy? Yeah. Delta U is equal to the negative integral of the force dot ds. In other words, you do work, right? This is the integral of force minus force times distance. And that's how you go from force over here to potential land, right? You take the integral of force times distance. Now you'll notice that this is a force, or sorry, this is a vector, and this is a scalar. If you want to go the other way, force is equal to minus du ds. In other words, you take the negative slope of the potential versus position function, and that gets you back over here to force land, and that is a vector. Okay? So that's how you get back and forth between force and potential. Okay, now we also talked about potential energy. Sorry, that's potential energy, not potential. We talked about potential energy and its relationship to this thing called the potential, which is probably the most confusing part of this class. Why do we have this thing called potential? It's really weird. And the relationship was that U sub E, that's the electric potential energy, is equal to Q times V, okay? Well, that means that if we have some potential and we put some potential energy, and we can tell what happens to a charge in this potential energy as we move around in this field, okay? And we define this thing called the potential by dividing whatever this energy was by Q. Now, this is a weird quantity, and let's talk about it a little. What it is it is this scalar field that permeates all of space around a charge. It's related to the electric field, but unlike the electric field, it is a scalar. Now, these guys, right, these two are global, and these two are local. These two are scalars, and these two are vectors, and they're all related in this weird way, okay? So how do we go from electric field then to potential? It's the integral of the electric field. It's analogous to this right here. Oops. Okay? Looks similar? It is. So if we integrate this electric field over some distance, that gets us over here to our potential. Likewise, how do we get from potential over to electric field? There's an analogy to be had to this. That's it. Okay? Now, this chapter, chapter 29, it's all about this right here, these two. Chapter 28 is all about this right here. chapter 25 through whatever, through 27 was about this right here. So we're filling in all these pieces of this relationship. So let's talk about these guys right here, going from E to V and back. All right, so the first thing right here, delta V equals minus the integral of E dot ds. The first thing you can get out of this is if I give you some electric field versus distance curve, you can tell me stuff. Now remember, we did something in class like this. I had some x distance in centimeters. I had some electric field in the x direction, and that's in volts per meter. And then I had some function that looked like this. This is 1, 2, 3, 4, 5, 6, and so on. Something like this. Okay, so that's the electric field in space. We go 1 centimeter. Then we have this negative electric field. That means there's some electric field pointing in this direction. Then we go for 2 more centimeters and the field drops to 0. So it's a constant electric field in this space. Then we have another constantly 0 electric field for 1 centimeter. And then we have a positive pointing electric field in the x direction for the next 2 centimeters. So that's what our electric field looks like in space. And this has some value. This is like 200, this is negative 200, something like that. Now this right here tells us that the potential is the area under the E versus S curve. Okay, S meaning some generic direction, some distance, and that's what we have here. So all we need to do is find the area under this curve, and that will tell us what the potential is doing. So we need the area under this curve and the area under this curve, only it's the negative area, right? So this is somewhat analogous to the relationship between position and velocity, where in order to find the position, in this case the position would be our delta V, and our velocity would be E. Well, we need to integrate the area under that curve, and in this case it's negative, but it's the same game, right? In order to find out what this looks like, we take the area under that curve. So now we have some V, and that has units of volts, and we need to figure out what this looks like. 1, 2, 3, 4, 5, 6. Okay. I'll drop down some little markers here so that I know where the important points are. Okay, so I have some negative area here. What does that mean is my voltage is going to be doing? Well, as I go along here, I need to integrate. So here I'm adding some chunk of negative area. That means my voltage is going to go up by some positive negative value. All right, maybe that looks like this, right? In this next chunk of time, I go up by the same value. What does that mean? That means a constant upward slope. So that looks something like that. In this next chunk of time, there's no electric field. Anytime you have no electric field, that means that the potential doesn't change at all. So you remain at the same potential all the way across here. So here we go like that. Okay? It doesn't affect the potential, it just stays the same. And then here we have some positive chunk of area. It's the negative integral, so that means we're going to have some downward slope like that. So that's what the potential is going to do. And if you actually find what the area is, right, this is centimeters, don't forget that, you get something like this has some height of 4 volts. So know how to do this. I could ask questions about this. I also asked, in this case, what sort of a geometry of electrodes could cause such a pattern to exist. And that might look something like this, right? We have, here is 0. Let's see here, I'll just do tick marks. 2, 3, 4, 5, 6. Okay, here starting at 1 here, we have some negative electrode. Okay, and then over here for this. I'm not going to worry about spacing so much. I'll just draw it. Might look something like this. So here we have a negative electrode. Here we have some big positive electrode that spans this 1 centimeter right here. And here we have a negative electrode like this. Okay? Well, which direction is the electric field going to point? Well, here we said it's a negative constant electric field. That corresponds to this region right here. That's a negative constant electric field. In this region right here, that's inside of the conductor, we have no electric field. Here we have no electric field. Here we have some positive electric field. And here we have some positive pointing constant electric field. Okay? So that's an example of an electrode pattern that could possibly make something like this. You can also use this integral to calculate the potential. So an example of that would be if I have some point charge here, and we already know what the answer is going to be, but it's okay. We have some point charge right here, and it creates an electric field radially outward like that. Now in the x direction, which is all we really care about, because I'm going to pick this point P right here, which is some distance r away from this point charge, I can find the potential at that place by integrating all the way up from infinity where the potential is 0 to this point right here where I find my potential. So I'm going to add up all of that area under the curve, right? My curve, by the way, for something like this is my, let's see here, this would be E sub x versus distance, I'll call it x, okay? It's going to look something like this, right? What I'm doing is I am adding up all the area under the curve out to infinity to this point right here, and that gives me my potential. So that's what I'm looking for, the area under that curve. Okay, well, I'll start with this right here, minus the integral from E dot ds from wherever I'm starting, which in this case is going to be out in infinity, to wherever I end up, which is at this point right here. Now the electric field extends beyond here, right? It just keeps shrinking like that. Okay, so to find the potential, we start at x equals infinity, where E and V, by the way, equal 0, and we're going to integrate to this point R. So that looks something like this. We get V equals negative the integral from infinity to R, E dot ds, and ds is going to turn into dx. So I'm going to erase that right now, and I'm just going to say that that is dx vector. Now, E and dx, well, which direction is E always pointing? Radially outward. What about which direction is x pointing? Same direction, right? E is always pointing, since this is on the x-axis, and E is always pointing radially outward, and X, as we have it, is also always pointing radially outward. So E and X are always pointing in the same direction. So E is parallel to dx. That turns this dot product right here into, well, it's no longer a dot product. We can get rid of the vector symbols and get rid of the dot product, and this becomes, I'm going to erase this right here, minus the integral from infinity to r of E dx. So that dot product goes away because they're always aligned. And if I give you a problem like this, that will probably be the case because I don't want to give you some crazy path integral that you can't figure out. Now, E, due to a point charge, that's equal to 1 over 4 pi epsilon naught. We're talking about E in the x direction because that's really what this is, times, let's see here, Q over, in this case, x squared. So that's what this is going to become. That's minus, actually, what I'm going to do is I'm going to take this minus sign and I'm going to flip my limits. So this is r to infinity of 1 over 4 pi epsilon naught times q over x squared dx. Now the only thing that's not a constant is the x dx, so everything else gets pulled out in front. The integral of 1 over x squared dx, that's pretty simple, and what you get is, this becomes, let's see here, q over 4 pi epsilon naught times minus 1 over x from r to infinity, which, lo and behold, becomes 1 over 4 pi epsilon naught times q over r. Well, that is the potential of a point charge. So we're good to go. We know how to do that. Okay? Variations of this. I could give you the potential, I can have you find the potential due to parallel plates, or maybe some chunk, some interval, or something like that. Yes?